Colloids. Colloids are sometimes called colloidal dispersion. So this is not quite a solution. It's a mixture in which we have a dispersed substance that's finely divided and distributed within this dispersing medium. The colloidal particles are small enough to stay suspended, but they're larger than typical solute molecules. Generally, solute molecules are almost roughly the same size as the solvent molecules. They're small. Colloidal particles are typically 1 nanometer to about 1,000 nanometers in diameter. They are small enough that they will stay suspended in the solution. They won't settle out. If you've ever made chocolate milk or hot cocoa, you know that if you let it sit for a few minutes, you have to stir it again because all the chocolatey goodness part sinks to the bottom. Those particles are too large and gravity pulls them down, just like silt in muddy water. In a colloid, the particles will stay suspended and will not settle out due to gravity. If we look at those particles under a microscope, and because they're larger, you can actually see them under a microscope, they have this jittery motion called Brownian motion. And so if we start here and were to observe a particle, we would see it kind of jumping back and forth. And it would just jiggle around like this, very random. And it's caused by collisions of particles. So why did it go a different direction here? It ran into something. Gas particles do this too. All liquid and gas particles have this Brownian motion. If you add soap to water, the soap mixes with the water and it stays suspended, right? But the soap particles are larger than typical solute molecules, and so they're actually forming a suspension. You get a suspension of micelles, and so we talked about this before, we talked about polarity and how does soap work. So we have here a soap molecule with its polar head and its nonpolar tail, and when there's enough of those, they will circle the wagons, if you will, and make these micelles. Now this is a two-dimensional illustration, but there would be three-dimensional and form a sphere. These particles are the size of colloidal particles, and they are held. They are stable, and they don't all clump together because there are electrostatic repulsions between the micelles. So we have this negative end of the ionic head, and that repels the other micelles. And so they'll typically form little micelles of a particular size. A phospholipid bilayer is much like a micelle too, except instead of forming a sphere, it forms a layer. Yeah. And so you have the polar ends on the outside and the hydrophobic nonpolar tails on the inside. And they're held together that way. And so it's electrostatic attractions that hold them together. So they're not chemically bonded to each other, but they do form a real layer that is functional. These micelles are large enough that they can scatter light. In order for something to scatter light, it has to be large enough for the light to interact with. We also see colloids forming with other things such as proteins, macromolecules, proteins, enzymes, things like that. There are many different types of colloidal dispersions that we encounter in everyday life. An aerosol, right? An aerosol has the dispersing substance, which is equivalent to the solute, is a liquid, and it's dispersed in a gas. So an aerosol can, you shake it, there's liquid in there, and you spray it, and a gas comes out that's got little teeny tiny particles in it. That's a colloid. You can also have solid aerosols where you have solid particles distributed in a gas. Smoke is tiny pieces of ash in the air. And you can see it because the particles are larger. Foam, like whipped cream, you've got gas dispersed in liquid, gas, air bubbles in the fat. Emulsions are where you have liquids dispersed in liquids. So milk. Homogenized milk has been treated so that the fat doesn't separate from the rest of the milk. It forms a colloid. The particles here are large enough that they block the light and you can't actually see through it. But you leave the milk sit and it does not settle out, it stays suspended. Raw milk from the cow will separate into layers, the fat and the skim milk. You can also have solid emulsions, and some of these are beautiful gemstones like opal. This is water dispersed in silica glass. What's known as the Tyndall Effect is the observation that colloidal dispersions scatter light. Some colloids are clear. They're translucent. You can see through them. But you can identify them as a colloid by shining a light through them. So here we have two containers with clear liquids in them and a flashlight. And we're shining the flashlight beam, and we can see the beam in this solution. We see the beam because the particles are large enough to scatter the light. In this solution, we can't see the beam. The particles are too small to scatter the light. This is a colloid. This is a true solution. You've probably all observed this. My house doesn't look nearly as grand as that, but we have dust in the air, believe me. And the sunshine streams through the front window, and you see this beam of sunshine. You can't see the beam of sunshine outside necessarily, but here it is in your front hall. Why can you see it here? Because of the dust particles suspended in the air. There's the end of chapter 12.